Good morning. Well, it's time for descriptive differential dynamics. And it's recently a bit more of the philosophical foreground, but in the course, circuitously throughout, the discussion and the dialectic of all the things of the descriptive differential dynamics is kind of like the elements after our theory of an entire theory, a theory, which I also call a theory. Says for the letter A, it begins things. Its usual kind of course in the foundations. So what I thought we might discuss today, or that I just kind of ramble about, that I would extemporaneously provide a certain amount of discourse and with regards to that which helps to fill the context, to provide a narrative, to refer to common understandings of the knowledge of the things, is then as with regards to how these kinds of things go, what there are to consider for descriptive differential dynamics, including a philosophical foreground. So today we're in the stacks, and so I'll just kind of continue in the stacks for that being a usual kind of source to help provide a thing. And so let's see here. What this is a book on radar and sonar, and it was briefly considered a little bit before. And so this is a pretty relevant work for anybody who's studying the field that is under signals intelligence, and the information is according to signals of radar and sonar. And so kind of like the maser was invented first, and then the laser. And then the after the acoustic and Mach and these kinds of things, then via in electromagnetic waves and reflections, then there's radar, and then sonar is the same kind of context in the acoustic models of the things, that the phonon and the sonon and these kinds of particles or what we talk about, how they have their instances of their events, that everything in physics is an event kind of things in terms of state and change and connections and actions. That this book on radar and sonar is part of a series called the IMA Volumes in Mathematics and Its Applications. So other volumes in this series include homogenization, effective moduli materials, and media. So moduli of materials is kind of like the bulk modulus, and we have stresses and strains, and then we have the those tensors related to them, which are quantities and variant under their vectors for tensorial products, which preserve the analytical character under the products. That then we had a lot of talk about that in the Morgan and the nonlinear electromechanical effects and applications to help provide the background of this kind of field in terms of waves in layered media, which is really kind of my goal, is to understand waves in layered media vis-a-vis the wave theory, the particle theory, and the resonance theories and such. So then you get into oscillation theory, computation, and methods of compensated compactness. Again, kind of helping reflect that there's the elastic and inelastic and deformable and non-deformable in the Newtonian liquids, the compressible and incompressible, and about how we have the notions for our impulses and the classical relations of things like force equals mass times acceleration, that it's usually in the perfect, in the incompressible, vis-a-vis that really it's in the deformable. Like if you've ever noticed that when you hit a golf ball with a golf club, for the briefest of instance, it totally deforms in context of its space and gets squashed and crushed and then flies off as it reconstitutes. It's real. That these are the kinds of things that help to relay, at least as like when we're building a bridge, it's static to loads in accordance to tensile and compressive, that we can figure out the strengths and design things at least twice as strong as they need to be so it doesn't break. Called engineering. Metastability and incompletely porous problems. See, this helps reflect that volume. Would probably be pretty interesting if you want to get into how to find the underdefined and fill it out and carry it out. Dynamical problems in continuum physics. Yeah, it's all about the continuum mechanics. Theory and application of liquid crystals, amorphous polymers and non-Newtonian fluids, random media, percolation theory and ergodic theory of infinite particle systems, hydrodynamic behavior and interacting particle systems. This gets into the notions of the random walk and about how particles are like. So you kind of have the ideal gas law, and then you have Boyle's gas law. And they're a lot related to stuff like the thermodynamics second law and thermodynamics first law, which are so different, and reflect basically that for a time and place in the empirical that was all about water and steam and the heat cycles of those, and the triple points of water in terms of their freezing and boiling points and their changes of states of matter. These were the available tables of the day that you could use to look up in a table, given values, what expected results would be empirically. And now we have the theory of that is really pretty clear cut and well understood for stuff like thermodynamics second law, whereas stuff like the thermodynamics first law gets in all sorts of other things related to it. Amorphous polymers, non-Newtonian fluids, random media, percolation theory and ergodic theory of infinite particle systems, hydrodynamic behavior and interacting particle systems, stochastic differential systems, stochastic control theory and applications. So the stochastic is that with the statistical or the random. It's basically is the idea that there is an element of the random in things, vis-a-vis that the differential is kind of that according to this system of equations and inequalities and the differential terms and the forms and the operators, the results there are the things. So in one way, I imagine having the stochastic and the differential together gets into things related, for example, the probability theory we've been talking about, or stuff like Markov chains vis-a-vis Monte Carlo. Whereas Markov chains in the ergodic is like, according to the law of large numbers, how will something behave over time? And the Monte Carlo is like, well, how many darts do I throw at it according to the given shape that I pretty much can, see the donkey or whatever after it's kind of sorted out and filled out. Monte Carlo is a means of building a model of random walks, basically. And then it's similar how that kind of stuff is applied in numerical methods like Newton-Raphson or otherwise. Like how do we make an estimate, a guesstimate, and then jump to either side and help reduce the problem to space? It's like I was reading this book I got the other day, and it's called the Approximation Algorithms for NP-hard Problems. So for a lot of NP-hard problems in space, they're not in the polynomial space in terms of times. They're in exponential space in time, the runtime of these algorithms. Then there's lots of approximation algorithms that basically say, well, actually we can break it down pretty hard in a lot of these, whether polynomial and non-polynomial don't have for various distributions and various configurations of problems, lots of ways to break them down, which they do. It's an entire field, and that book, Approximation Algorithms for NP-hard Problems, is quite a bit that goes on into that field. Hydrodynamic behavior and interacting particle systems, stochastic differential systems, stochastic control theory, and applications. So a large part of this stuff with regards to why for engineering is control theory. And so control theory is the idea of like, well, we got a plant and we got a feedstock and it's coming in, and so we don't want it to blow up. Controls. Numerical simulation and oil recovery. Yeah, the mineralogists and that have a lot going on. Computational fluid dynamics and reacting gas flows. So there's fluid dynamics and then the computational fluid dynamics, and there's flow models in networks like our graphs that are discrete and connected by edges, and then there's flow models in the fluid models that are kind of similar. So you get into like Ford-Fulkerson is the algorithms that basically define how things flow in a network. And then for Navier-Stokes is what we do that in the continuous media. If you've ever thought about or heard about the magic square, the idea of a magic square or Latin square is the idea that all the rows and columns add up to the same value. So this, like if you take a 5x5 square and then any one of these rows and columns, they're just numbers in it that add up to the same value. So if you think of uniform continuous flow across a surface, you're like, it's always steady and it's across a surface. It's what we call current. It's the whole idea of the fluid model of electricity and water and fluids under pressure and all their terms. So the idea of this magic square is like, well, when you think about stuff going over a surface, it's never actually just continuously pushing across. It's wavy. It's got its vortices and eddies. So the idea is for all the family of magic squares, whatever they could be, that those basically model it's like, well, if you have a flow here, it's still got to be the same continuous flow vis-a-vis that anywhere on the part of it, it varies, and it's even can be negative. It's back and forth. This gets into the whole thing like when we were talking about a theory of heat, and Scheller, and these ideas of the flow of that, and things we got into, and there's basically quibbles or discussions about when things are decided to be this one way for their completeness and determining their forms, that there is this other thing. What happens when it gets when it's anything less than ideal, but it's still perfect somehow? That the idea is this Latin squares and magic squares make a model of vorticity and eddies and flow to build models of those. The idea being of finding completion results in those, which basically then have that it's a thing, and it's something that people are familiar with, elementarily in the functions. Like, yes, I've solved a puzzle, which was to add up everything, the same. It's the same in any direction or however you still slice it, but it still just results, one constant when we think of it in terms of a big long stack of those that add up all together. Magic squares, mathematically. Computational fluid dynamics and reacting gas flows. So you see. So volume 13, numerical algorithms for parallel computer architectures. Parallel computer architectures are any means you implement it's called systolic. So you got a clock chip, it's a crystal, it oscillates a resonance and a frequency, and it drives these traces into the chip. And so as that goes along, then the idea of the parallels, you can have any number of units wide, and superscalar then it's called, and it goes out. All driven by one clock. That's called the systolic. Like the beating of the heart, the beating of the chip, the timing is that. Mathematical aspects of scientific software. Well, mathematical frontiers in computational chemical physics. So molecular modeling is there's systems like Amber and Chime and a couple other very well-known in the industry molecular modeling softwares, and these are what are used to help make the models of reactions and according to the active sites of ions, basically. And so what's going on with that has been a long ways coming, and stuff like protein folding. How does it fold? What are the active sites? The physical type of thing, like the pinchers of the zinc, and the active sites and these kinds of things. Vis-a-vis hydrophilicity. Water is a universal solvent. Well, how does it work? Because it's also highly polar. Science is still just barely learning some of these things on the very fundamentals. Mathematics and industrial problems. The idea is often and usually to arrive at the formula and to find error modes, which then demand controls. Applications of combinatorics and graph theory to the biological and social sciences. So graph theory is basically discrete, and flow, computational flow or fluid dynamics is basically continuous. And it reflects state and change with conservation and all our laws. It's called the laws of physics. It's a theory. It's a theory. Q series in partitions. So Q series, I'd imagine, to be series of a particular form. If you really want to know something about the series of numbers, there's this online encyclopedia of integer sequences. And so N.J. Sloan and peers have made a online encyclopedia of integer sequences. So any kind of integer sequence that like Fibonacci numbers or the integers or squares or hexagonal numbers, they've assigned them a name and have a search engine for them, so that when you encounter a series of numbers that are integers usually, you can put it in this tool and help find all these related works and descriptive terms that apply to it. So it's one of the greatest things. Invariant theory and tableau. So invariants are the symmetry issues. Either way, they kind of come back either way, meaning they affect and reflect a symmetry. An invariance reflects a symmetry. It's got a conservation law, and it's got a continuum laws about it. And then the tableau is then like well, when we have a tableau, it's a table. So when we have that in a matrix form, and we want to figure out how that symmetry affects and reflects then how we have this model of elements in a matrix, how do they get so affected by these? What are the rules on this one that make strokes? On this rule, the other that makes strokes. And so you can have definitive terms and how then it's possible to find a means to compute something in a very direct kind of way, and on the data structure. So it's into data structures vis-a-vis lemmas, their terms. Volume 20, Coding Theory and Design Theory, Part 1, Coding Theory. Volume 21 is Coding Theory and Design Theory, Part 2, Design Theory. So coding is a kind of overloaded term because symbols are codes and codes, coding are data structures. In signal theory and information theory, a code represents a word, oftentimes, or elements of a language of signals. And then we have like error detecting and error correcting codes vis-a-vis the rising and falling edges and latches of what are the devices that can kind of detect changes, in time series data, these things. Then the codes also reflect like a coding table, like the Huffman codes, and then there's arithmetic coding for entropy coding, which is to compress things. You analyze and discover its content and the distribution of its elements, and then are able to create a graphical and pictorial representation of that as some other codes, or vis-a-vis that various binning and bucketing, you're able to fit it into a smaller constant. There's what most people would encounter in entropy coding is the Huffman table. So what the Huffman table is like you take any text and you find its most often occurring word, and you give it the shortest constant. So over time, as the symbols arrive, the most commonly occurring thing gets the shortest code. And then correspondingly, you sort those and you make it so that then out of the alphabet of the text and the language of the text, you get this alphabet and language of the codes. And so according to however it is so arranged that maybe it's like longer words or more often or this or that, out of this table, a dictionary of the terms, you make what's called the Huffman table, and it's well known to be the optimal way to compress something. There are pretty simple results that in entropy coding that's a thing. And then when you get to stuff like transforms and stuff that help represent data that is lossy compression, like in the imaging and compression, like this video or anything you see on the internet that's continuous tone or anything that isn't lossless compression, then there's lots of stuff that they use that's used that to keep stuff within the perceptual bounds, what the human eye or ear can't really tell the difference. And then the result number is that then that has applied entropy coding, which is usually Huffman coding or various kinds of arithmetic coding, where you make an algebrization and a geometrization of thing, where that basically gets into operator overloads and how things have their minimal models that all together encompass all their detail and have with the notions of these strokes and how the clock can drive systolically a computation in one of these units of computation, that it crunches the thing. Most of the computing that goes on in widely distributed network applications is compression and encryption. So generally for any channel in signal theory and information theory, it's considered how to apply compression and encryption to it. Volume 22, Signal Processing, Part 1, Signal Processing Theory. It's waves. Volume Signal Processing 2, Part 2, Control Theory and Applications of Signal Processing. It's squeezing the waves. The design of antenna. The notions from electrical engineering of the pickup or the amplifier or the op-amp. These are things you learn about in signal processing. Volume 24, Mathematical and Industrial Problems 2, Solitons in Physics, Mathematics and Nonlinear Optics. Now that sounds pretty ambitious. Because solitons is like, well, we encompass a state, and when we have something like an impulse, we think of it as a straight, direct linear impulse. It's what it is with a soliton is the wobble. Weebles wobble, but they don't fall down. Volume 26, two-phase flows and waves. So phase is an important thing, and I wish I knew it better, because phase involves all these kinds of things that get into the content and character of otherwise a traveling wave, with regards to how it's got basically a vorticity in it. It's got phase and how it so affects phase. And this is for things. There's two basic concepts in electrical engineering of these things. There's digital engineering, which most people know is like, this is what drives my chip. Then there's power engineering, which is, this is how power, according to electricity, moves over the wires. Everything from the conversion of mechanical heat or otherwise energy in a potential form to electricity, to the conversion of that back to anything else. So power electronics and digital electronics are two different sorts of fields, but it's really one thing. Nonlinear evolution equations that change type. Now, this reflects systems of equations, and it could be very broad, nonlinear equations that change type, and it helps reflects the categorization and how things are and how they go and how to consider them in a formal sorts of manner. Computer-aided proofs and analysis, multidimensional hyperbolic problems and computations. The hyperbolic and hypergeometric. Get into the hyperbolic is basically just a complement to here the identity dimension, because it's 1 over x, y over x, x over y, and this kind of stuff in terms of the identity dimension being x equals y equals z equals ... and having that as a framing for projection and perspective, this thing. So the multidimensional hyperbolic problems gets into the hypergeometric, and also it gets into the hyperbolic analogs to the trigonometric functions. So sine and cosine, there's sinh and cosh. Also, that these are very well explored and very well understood and tabulated to a very high precision to all these kinds of things. It's engineering, it's physics, here that it's that kind of like physics is like, well, we settle on thermosecond law because for entropy and everything must fall down, then it works out great, and we have stuff like the Fourier style analysis, and it's great and all this kind of stuff. And then for the variations is about these other aspects. So the adiabatic and non-adiabatic is how it's usually phrased these days when they try frame these kinds of problems in terms of helping to solve them and to get where from things are nonlinear to where they're linear or have close forms. So, Volume 32, Radar and Sonar, Part 1. Okay, so that's this book. And the forthcoming volumes, it says, back in 1988 and 89, they were going to have nonlinear waves, robustness, diagnostics, computing, and graphics and statistics, dynamical systems and their applications. Oh, so now dynamical systems that's all we've been talking about this whole time, is differential descriptive dynamics or descriptive differential dynamics. Twist mappings and their applications. Dynamic theories of turbulence in fluid flows. So this gets into stuff like the hypersonic or whatever, and what happens to the interfaces of things and vis-a-vis how they deform or not. If you had a 200-mile-long maglev train and accelerated at about 1 or 2 Gs, or according to 1 G is equivalent to the acceleration of Earth's gravity. And so if you accelerated over that and just kind of pointed it up, it would launch all the way to space and be gone. It would reach escape velocity and be gone from the Earth. Summer Program 1990, Radar Sonar Part 2. time series and time series analysis, phase transition free boundaries. So as you can see, such a work like this is part of these greater works in the stacks. And then a particularly good solid volume of an edition of a series like this is the result of primary science in the United States for a long time, this kind of thing. So we got surveillance and remote surveillance, the idea being that radar is for remote sensing. So remote sensing encompasses the idea of everything from vision to any kind of means of the apparatus of the perception of things. For example, from satellite imaging, it's remote sensing. Radar, it's remote sensing. Cameras, remote sensing. So it's in optics has the notion that light travels according to geometric objects and what they call them optical optics. Light is geometrical and optical. So the idea of how something like radar waves and anything that's a wave in the media is kind of associated with that as well. But while that is so, and we have this whole theory of electromagnetic and then like higher frequency and lower frequency, about the ultraviolet down to the infrared, that the infrared is kind of closely associated particularly with the kinetic and the notion of heat in the infrared. The ultraviolet is associated again with kind of just the other side of the edge of what's really the visible light. So visible light is really kind of privileged in terms of otherwise what's affected by the electromagnetic and what's affected by the kinetic in terms of radiation, as we've been talking about the nuclear model, radionuclear model, and light and optics vis-a-vis charge and the kinetic. René Descartes is famous for his philosophical works. But he might not have been so famous if he hadn't also been very studious in physics of the day, and when they're trying to reason why a rainbow has its colors, red, orange, yellow, green, blue, indigo, violet, Roy G. Biv, the spectrum of colors, and the angle of the rainbow, and under what conditions in light and the contents of the air in the medium of the rainbow. Carl Boyer's got a great book called The History of the Rainbow, and in it he declares how Descartes basically was able to stand up one of the best approximations at the time. He had the best numbers in his theory. And then later it goes up into like Fresnel and Airy and these people who have brought us the theory we have today. So I'd read a little bit from this before, but I'll get a little bit back into some of these things later. Badiou. Now this is a philosopher, being an event. So this is a guy who's trying to make a modern thing with regards to the errancy of excess. We shall show that the measure of p omega naught can in a generic extension S sign surpass an absolutely indeterminate cardinal sigma given it in advance. So I'll have to look at this a little bit more because I'm very familiar with set theory. And if you want the tome and the mountain on set theory, it's a book called Thomas Jech's, J-E-C-H, Jech's Set Theory. And then there's any such things as about foundations of mathematics and stuff there, that there's foundations, new foundations after Quine and all that. But Jech is the man. And then there's Moschovakis' axiomatic descriptive set theory. So you got set theory and descriptive set theory, or Jech and Moschovakis. So those are the authorities in regular and ordinary set theory. So this guy gets into a bunch of stuff about the infinite, and I already have one. But when I looked at that a little bit before, what I was looking at is that it's just kind of for the digital, and so it makes some things. He says, "Oh, infinity finally defined. That there exists a limit ordinal is our second existential assertion." So all that is Russell's retrothesis. So. We have not yet defined infinity. Well, that's too bad. The law of the hazardous detour. Here it's just the inductive impasse. The structural fault which opposes. Well, I can understand Badiou's struggle because it's quite a ways to the top, and it's fraught with wrong turns. But I'm going to look at this some more. Now, I hadn't really noticed that he's really trying to stand up some usual kinds of things, and I'm not quite sure. This is pretty new, from what I understand. I just got this, and from what I understand, there's something going on in it, but I think what it really is it's just another kind of it's usually conservative, and so if you want something that's just conservative already and it's figured out, you got Edward Nelson's internal set theory. So Edward Nelson already made for internal set theory a way to kind of like keep the tent up or prop it open. And then some of his later stuff, he was trying to prove ZF is inconsistent or something like that, and that didn't really work out for him too great. But it's an approach, and it's the thing. So let's see. This is what we got here. So Alain Badiou. This was published 2006, so it's been around longer than I knew about it. But I'm not. I think it's pretty much a conservative thing. He does get into deduction at least. The impasse of ontology, he says. Yeah, this is kind of backdated. Theory. Well, all right then. I'll deconstruct this more thoroughly. On difficulty, this is where we left off. We're reading from our stacks. And it's social, it's about literature, it's about text. Cliché. Cause célèbre. Cliché. Whorf, now Whorf is mentioned, W-H-O-R-F. There's a man named Whorf, and he's got some interesting things in the deconstructive theory. Whorf's conclusion is famous. Though only the expert is qualified to deal with these analyses. Well, who? Yeah. Moreover, if the Sapir-Whorf hypothesis were correct, if languages were indeed monads with essentially disparate meanings of reality, how then could we communicate interlingually? How could we acquire a second language or traverse into another language world by means of translations? So it kind of reminds of Gadamer on Heidegger and the Greeks and being able to see through the lens. And it's like, well, we can never see through their lens. We're different. And so it's like studying another language. It's like, well, yeah, another language is essentially an alien language. How can we communicate with them? It's like the Chinese room in the philosophy of the thought experiments. And, well, it just makes a bigger one. You know, that's the whole point of deconstructive analysis and objective analysis, is that there is this kind of thing. And we have from Kant and Hegel that they've kept inside in the shelter of the elements that are considered good philosophy are allowed grounds for a theory already. Grammatical universals. Grammar and the study of language is a great, cool thing. My favorite book about grammar is this one by Colm, and he helps break down all the parts of speech in English, and especially its very rich lexicon and application of the copulas, which connect things like is, what is in words. So it's extensionality and intentionality and these kinds of things. The philosophical discourse of modernity. Habermas. Well, this is more Habermas. Now, I was reading Marcuse in The One-Dimensional Man, and it's kind of sad, you know. It's because a lot of it gets into the angst or the zeitgeist of the turmoil of the change in society, and as well that he talks about man and the human condition and the dehumanification of man by machine or the system, or what you might want to term it. But it can also be read as fairly well, good man. You know, I like to think about it that way because I don't really care for angst. Heidegger no longer wants to think the totality of finite Dasein ontotheologically out of an empowering relationship to some highest entity or to entities taken as a whole, but rather only out of itself. That is, as a self-affirmation that's paradoxical because it's without any basis. See, if you follow what I been coming into his philosophical foreground, and why is there something rather than nothing, or as Nozick puts it, what is the fundamental question of metaphysics? This entire sort of approach that's kind of afterlogical positivism is exactly what Kant and Hegel actually left in the theory, the sublime. And for Hegel, I'll have to find exactly how we want to phrase this teleological for the ontological. That what happens is the received tradition then doesn't really have that in its arsenal or in its gamut of concepts, conceptually, that is still really a thing. And so it just negates what he just tried to read from Heidegger. Heidegger, anyways, you can look through Heidegger and find 10 different things he says because he just spouts off readings of the Greeks. And so just like anything else, it's like they say about the Bible, it's a big enough work, you can find it to say whatever you want it to say. Thus, we establish an actual overall analysis and treatise and treatment of it. Begins. We're reading it, you know. To be sure, the latter no longer appears in the shape of an omnipotent ik, primal I, but still as the ultimate pursuit of human existence. Well, no, the universal is just kind of our grounds for universal existence. To Dasein is ascribed the authorship of the projecting of the world. Well, that's just a theory. Everybody's got a theory. Everybody's got a psychology, and it doesn't work on everybody. Why fundamental ontology had to run off into the blind alley of the philosophy of the subject it was supposed to be steering clear of is easy to see. Ontology with a transcendental twist is guilty of the same mistake that it attributes to classical epistemology. So is teleology of ontology. So yeah, many of the modern logical positivists, and as kind of was described before, kind of adrift in a sea of their own making, which is not really of their own making. So it's still very rich, though. It's still quite a thing. So this is I looked at that before. His books, I looked at these before. What is this here? The Poem of the Cid, El Cid. So this is actually just some poetry, and it's about 1098. So it's just a history of sorts. Speculations of T.E. Home, the Automotive Handbook. These are, again, some other ones we've already kind of looked at before. Zen, more Zen. C.S. Lewis's Mere Christianity. So this is, C.S. Lewis is most familiar for Narnia and Aslan and, The Witch in the Wardrobe and stuff like that, and Aslan. And, but here he does a really great job of making for apologetics and for even, like, for example, when Christian theology was used to justify bad acts or something like that, it's he makes a great kind of an apologetics for it, and helps to kind of extract what is some of its greatest in spirit, and for the spirit, for the soul. Lucid apologetics. The Book of Five Rings. This is basically, it's kind of Machiavellian. I had sword techniques. The Japanese swords, they have what's called the daisho, the long and the short. And so you got the katana, and then you got the dai katana. It was a longer katana, and the wakizashi is a shorter katana. Together they make the longest short. So the idea is that basically with those, then you can make a big sphere about yourself, called the waterfall, water wheel. So this is basically the school, the Book of Emptiness, Ku no Maki, the Book of Emptiness. 30 spokes will converge in the hub of a wheel, but the use of the cart will depend on the part of the hub that is void. So this is like for the Tai Sabaki and the Satori. Satori is like when we're talking about psychological experiences and like epiphany and rapture and these kinds of experiences and moments. Then there's the Satori and the Kensho, and the Satori is like the Kensho is the Satori of the sword. And so this is kind of a thing that is part of the theory of arts, these things. What follows is a brief philosophical discussion to prepare you for the final chapter of the Book of Five Rings, the Book of Emptiness. Philosophers have forever been inquiring into the nature of reality. Basically, arguments have been over what is real, that is, what can be said to exist. For instance, we might all agree that this book exists. You can see it and touch it. But what about beauty? Does beauty exist in the same way as this book? For this, we can look to like Kant's judgments on aesthetics and these kinds of things. No, you can see or touch a beautiful thing, but not beauty itself. So he's describing it's an ideal, which is great. Would it be correct to say then that beauty does not exist? No, because then when we talk about it, we all know or have some idea about it, so it exists somehow. So if it does exist, where is it? Some say it only exists in your mind. And like, for example, we were talking about the Descartes and the Dalai Lama and that beauty is only a human conception, a human description of real things, used in the same way as when we describe something as red. Maybe it would be safer to say that beauty exists in a different way than this book does. So that's the whole idea of Platonic ideals. A chiliagon is a 1,000-sided picture. You might be more sure if we were discussing a 3 or even a 10-sided figure, because that is easier conceptually. But this chiliagon is impossible to envision. How about unicorns? The Zen Buddhist view of reality is neither subjective nor objective. It is. The Zen view, as always, is a practical one. The traditional Zen Buddhist view, nothing in the world ever is. It is always becoming. So this jibes really well with the Greeks and their theory of aletheia and dialetheia, and we only ever kind of disclose or uncover things. Lethia is like the river, like Styx. You get dipped in Styx, you become immortal. You get dipped in Lethia, you forget. And so aletheia is like, I remembered. It's like remembering something for the first time. In the Shingyo Sutras, chanted by the Zen monk, each morning appears the following. Form is her emptiness. Emptiness is form. Form is no other than emptiness. Emptiness is no other than form. That which is form is emptiness. That which is emptiness is form. Exactly the same as Kant and Hegel and sign and no sign. It is the relationship that is, not the things that relate. This relationship is que. Musashi says that which cannot be known is Q. Well, to posit beauty or book or unicorn or chiligan is to have your mind stop. To think of death when you are faced with your enemy is to have your mind stop. This is why the swordsman must remain detached from worldly thoughts. Unun Muso takes on new meaning. If you can read yourself with a stopping mind, you will achieve satori and experience the movement as if it were your own. So that's being in the moment. Satori. That was a stack of books. One of the important practices we learned growing up is that you have to be able to sit with like a book on your head for an extended period of time. With the general idea being that as long as you do, you're kind of maintaining good posture and form and this kind of stuff. So this is one of those things that we get into, trying to figure out the things. All right. Number 3. Well, we kind of looked at this before. History of the circle. Now, this was up quite earlier when we were looking at this. And here's the deconstructive criticism, which when we were looking at this with regards to the philosophical foreground and also the importance of a critical deconstructive account of things to understand how things are and how they go. Yeah, this is the stack we've already kind of gone through. Here's Nozick. We were talking about philosophical explanations. Why is there something rather than nothing? Robert Nozick addresses why is it a question at all, and it's over time historically why Leibniz says so, why the Mishnah says so, why it's the very biggest deal in metaphysics, and also we might talk about how the Bible starts that way, and most books establishing an authority philosophically all start the same way. There was something. Probability theory. Howard G. Tucker's probability theory, a graduate course in. Topics in physics. Oh, here's Lefschetz. Now, so Lefschetz will speak to the algebraic geometry. Let's see what he says here. Yeah, we'll find something kind of readable. Topological relation, VP, back and forth from R squared, assigns an exceptionally simple topology to VP. Let the edges of D oriented from the origin ought to be designated by 1, 2, ... 2P. Any I sub h defines a one cycle represented by the sequence I sub h. Any two edges I sub h, I sub k define a two cycle represented by the pair I sub h, I sub k, etc. I sub h, I sub k, I sub h less than I sub k form a base for the two cycles of VP, etc. I'm mainly concerned with the two cycles. So in counting arguments is how we build all manners of classical probabilities. And it's like, well, out of the combinations of 2d6 or two six-sided dice, what are all the things, count up what they could be, and it helps reflect it then for the sums that they have this thing. So then there's the choice function is how many ways can you pick so many out of so many more, like, and choose k, how many ways are there to choose k things out of n many. And so then Stirling is this great guy, Stirling, and he introduces the notions of the cycle and subset numbers, or Stirling numbers of the first and second time. And so these like, well, how many cycles can you find under the permutations of these things that repeat? Or how many subsets can you find? It's like, how many ways can you find that you can find subsets of this from the other? And so they're also called type 1 and type 2 Stirling numbers. And Donald Knuth is one of the most famous modern guys in the field of concrete mathematics. For example, for his book with Graham, Knuth, and Patashnik called Concrete Mathematics, or The Art of Computer Programming, where he defines a computer in a language and then goes into explaining the runtime of all sorts of algorithms that are very fundamental. Basically, sorting and that's it, and like tape merges and stuff like that. And it's got some. They're great library quality books. There's a couple foldouts that show like here's how we make it so that we have all these different tapes of all these supercomputers, and we're able to kind of like move them back and forth and do something that would otherwise be too big for what we do. So anyways, in some of his fascicles or notes, he's got this one note, and Knuth writes about a guy named Iverson's language called APL, a programming language, which is really kind of like the terms are algebraic and mathematical. And then the other part is about this Stirling cycle and subset numbers. So just like Lefschetz here started to detail, just by this structure, you can build it up, you can make some arguments and show how these things hold, these relations. Then as far as the relations hold, then it makes things, after they're sensible and fungible, and then to get to tractable forms. Topics in contemporary mathematical physics. So this is great. Caius Lamb has made, this is a graduate textbook for people getting into study of mathematical physics large. I mean, it kind of has to combine theories of relativity, the quantum theories, and all this stuff together. Talks about, for example, permutations, sine and sine. How can we figure out the symmetric and skew symmetric, symmetric and the covariant and the contravariant, even and odd. Building these things out as these make up in the operators and the forms up above, how it gets to be a thing. Identities, flavors of quarks. The idea of quarks is that subatomic physics has a molecular model and a nuclear model, and what's in it is neutrons, protons, and electrons. So what are in those are quarks. And then the idea of technicolor is that those have quarks, those have quarks, those have quarks, and it's quarks all the way down to infinitesimals, all the way down to superstring theory is the model, the conceit, the quantum theory. That's how it is. That's kind of how it is and how it goes. Moving frames and curvilinear coordinates in R cubed. Partition of unity. Equi-partitioning is this idea of saying, okay, we know we're looking at like a flow or a thing. So equi-partitioning is about the most usual thing is like, so we're gonna slice it. And then it adds up that it's the sum of the slices. Equi-partitioning. The integral on the right-hand side is the usual Riemann integral. This means that if g alpha dot psi with respect to the coordinate system x1 to xn and wi is expressed as g alpha dot psi equals h1 of x1 xn dx1 wedge dot 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 wedge dxn, then the integral on the right-hand side of 32.18 is given by the integral of over the wi of g alpha dot psi equals the integral of wi of this h dot 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 dot. So he's made a theorem relating a dot product to an outer product. It's like an addition formula. The great thing in mathematics, like counting arguments, is addition formula. It's like I have two exponents, one's to the power of m and one's to the power of n. What is their product? It's it to the power of m plus n. It's an addition formula. So these are the kinds of things that make closures, that make forms, that make things fungible, and then they also make it quite tractable. Vis-a-vis, like sometimes you make something fungible as like a numerical method, and then there's like a billion steps that you can carry out to get it a little bit closer. I mean, it's still tractable in a way, compared to like there's no traction at all. And then when it's fungible and tractable, it's like I got a closed form and it is done. So this is why algebraic geometry ends up being better to know if you only have the results and capacities of like the limited resources, vis-a-vis is like, well, we that's why we write Fortran, and the supercomputer is going to crunch this all year. Ubiquitous success of mathematics and physics. Well, so that's most of the stacks. So we're pretty much 3D stacks right here. Here's this nuclear physics. I'll set this back up again. This is one of these ones like Heisenberg's popularization, kind of like Weil's continuum, and that it's good that they focus on a particular subject that's deeply fundamental and help establish the requirements and desiderata of it because it has them. All right. What is this here? And then this was, of course, my favorite book for a long time was Out of My Later Years. And it was thoroughly read here in its own series. And well, this we'll get to some more later. Here's Mogan. So this will be back on the top of the stack. All right. Let's see. Figuring out how to just kind of a close for the day of this talk. It's a bright and sunny day outside. It's about the end of the year, so Happy New Year's again. And what I figured I have some travels coming, so I'll be away for a while or back and forth. It's pretty flexible for me, so I kind of I prefer as much as possible to make travels and stuff when other people aren't, because that way more road for me or that kind of thing. And then let's see. So and so far again, if there's something that deserves the attention of trying to figure it out, is the identity dimension is a thing. So that's great. It's just a way to assign particular coordinates to things. And so you might think of it as just like it's the XY plane, but I'm only looking at the positive quadrant, and then I draw a line called x equals y. And now I look at that and I say, well, that's the only line I have, but I happen to have framed it about these others. And then also I can kind of fold it out so it can make what's above and below that, and then it can make a half plane out of that quarter plane. Then the idea of that is like, well, when it's drawn in the quarter plane, then it looks like, squares intersect it at each point, 1, 1, 2, 2, 3, 3, each coordinate x, y, x equals y. And then that when you rotate that, or basically double the angle of the what's the basis? It's not an orthogonal basis. It's a orthogonal semi-basis. These semi-dimensions about what reflected the x and y build a framework to hold it. So it's very graphical. It's very simple. It's just what it is. And then there are many ideas how to make the identities for that. So what I'm thinking about the stop derivative is I can basically relate that to the hyperbolic, which is the inverse function, which is like it's a curve and it comes all the way down from infinity until finally it gets to 1, 1, and then it goes all the way out to infinity. And it's fills that line. But it's just not orthogonal at the basis. It's the most curved point at that point, according to its where the identity dimension or this line intersects it. So it's a diagram. So then the idea for the stopping derivative is related to that above and beneath that again. So as I was reviewing some of these talks a little bit before, and there's the stuff about the complex diagram, and it helps to establish a sort of deconstructivist account and a breakdown of the usual complex numbers arithmetic and how it uses division in the left-hand, right-hand side and these kinds of things, which are not Gauss's principal terms, but it's quite well defined that it's not well defined there, that I can build out a more definition in it, and it's kind of a thing. And so, and then for the stopping derivative is this idea about how to apply all this higher orders of acceleration and things, because as we were talking about in the linear and the nonlinear, and the compressible and incompressible, and the elastic and inelastic, and the diabatic and adiabatic and non-adiabatic, and all these different things that get into why science is able to consider things in what it has is closed classical forms and linear impulses, but what it really needs in terms of its context of the universe, the objects, and potential theory, that you figure that it will have a trace, or how it's drawn graphically and also directly. So as I've continued to kind of expand the notions of what we're already kind of gone past when we go from the just plain numbers and magnitudes to sign magnitudes to a diagram also of a plane after what are lines and these kinds of things, area and this and that, to take it back to that where it starts from, that it is an origin, that it is this identity, that these are these concepts that I feel will really be fruitful and that I would employ for what I would want to do, make for some more mathematics, because it's as simple as things can be. All right, then. Merry Christmas. Merry Christmas and Happy New Year's. And here's hoping that 2024 will be less of a circus than, 2020, 2021, COVID years and all this kind of stuff. And have a great day.